Dear children, taking some examples from integrals which are already in a very basic form. If you see the functions, look at the function, they are in basic form and can be integrated easily after a bit of simplification. So taking some examples of those kind, look at this part. We have to integrate this cubic polynomial which is getting divided by a linear polynomial x minus 1. So we will try to simplify the expression first and then we are going to integrate it. If you see in the numerator, factorization can take place. If I take x square common from the first two terms, we are left with x minus 1. And the later two terms are also x minus 1. So this entire thing divided by x minus 1. So the numerator is broken into sum of two different expressions. Now if these both be divided by x minus 1 separately, this is what we get. X square into x minus 1 divided by x minus 1. And then the later part, x minus 1 divided by x minus 1. So you can easily see the common factors can be cancelled out. So here we are only left with x square and in the second part we are only left with 1. So we need to integrate x square plus 1. So using the formula for integral of x to the power n, the integral of x square will be x to the power 3 divided by 3 plus integral of 1 which is x to the power 0. So integral of 1 comes out to be x plus constant of integration. Now look at the next one. Even if we look at this way, we will think that maybe it is difficult to integrate. But have a quick look, you will see that this expression can be simplified. We can write it like this, 2 over cos square x. And the later part can be written as 3 sin x over cos square x. And this entire term can be later on integrated with respect to x. Now if you look at the first part, 2 divided by cos square x. So 1 over cos square x can be replaced by sec square x. In the same manner, this cos square x can be written as cos x into cos x. So 1 of the cos x along with sin x. The ratio will be sin x over cos x, which can be written as tan x. And the leftover term, which is 1 over cos x, can be written as sec x. Now we can see the expression and try to make out, can we integrate it? We know that integral of sec square x will be tan x and the integral of sec x tan x will be sec x, because this is derivative of sec x and this is derivative of tan x. So they can be integrated. So integral of sec square x comes out to be tan x and the integral of tan x sec x comes out to be sec x. So this is the integral I. Now moving on to another example. See this one. It is product of two functions. One is sec x, another is sec x plus tan x. So again this can be simplified and then we can go for integrating it. We can multiply sec x with the terms inside the bracket which are sec x plus tan x. So let us go for the multiplication part and you can see it reduces to sec square x plus sec x into tan x. So it is taking the same form almost which we got in the previous question. We can either go for integrating it directly or you can write them, both of them separately in two different integrals, and then also you can go for integrating both of them. So you can see integral of sec square x is tan x and integral of sec x into tan x is sec x. So this is the required integral plus constant of integration. Now taking another example, you can easily see sec x is reciprocal of cos x and cosec x is reciprocal of sin x. So if we take reciprocal of both, sec square x can be written as 1 over cos square x and cosec square x can be written as 1 over sin square x. So this is what it is reduced to. So sin square x over cos square x can be written as tan square x. Now we are unable to recall tan square x's derivative for which function. So we'll go for a slight change here. Using the trigonometric identities, So tan square x can be written as sec square x minus 1. Now we can integrate them. We can integrate sec square x and we can integrate 1. We can integrate them directly in this form within a single integral symbol, you can see, or you can write the integral separately for them and integrate. Integral of sec square x is tan x and integral of 1 will be x. So this is the required integral plus constant of integration. So these were some examples where after doing a little bit of simplification, we were able to integrate the given function. Now let us derive some of the new results. Till now we are unaware of what is integral of tan x because we cannot recall, we are unable to recall a function whose derivative will be tan x. In the same way, a function whose derivative will be cot x. So we are going to use the method of substitution in order to get the integral of tan x and the integral of cot x. So we'll make slight change in the expression. See, the integral can be written as sin x over cos x. So we are converting tan x into sin x over cos x. And if you see carefully, you will find they both are derivatives of each other. In one of the case, the derivative gets associated with a negative sign. So that we have to keep in mind. Now over here, if I use a notation, say t for cos x, suppose I am substituting cos x as t, then you are converting the expression which was earlier in variable x, now you are converting it to a new variable which is t. So the operator needs to be changed. Dx needs to be converted in terms of t. So what we will do, we will differentiate both sides with respect to t. So if I differentiate the left hand side with respect to t, derivative of cos x is minus sin x. Now because the variable here is x and you are differentiating with respect to t, so the derivative of x will become now dx over dt. On the right side, derivative of t will be 1 because you are differentiating it with respect to t only. Now if this dt be cross multiplied, even the minus sign, we see that sin x dx can be written as minus dt. So you can see if cos x be replaced by t, then this sin x dx can be replaced by minus dt. So what is the new form of integral now? It is 1 over t. So 1 over cos x is written as 1 over t and sin x dx is written as minus dt. We can even write it as minus integral of 1 over t dt. So you quickly recall the integral of 1 over t. We know derivative of log t is 1 over t. So the integral of 1 over t will be log t. So the integral comes out to be minus log t plus constant of integration. Now you can go for replacing t by its value. T was cos x. So we can write it as minus log modulus of cos x in order to ensure this is a positive real number plus constant of integration. So integral of tan x can be written as minus log cos x, or you can also write it as log modulus of sec x plus constant of integration in order to get rid of this minus sign. How can you get rid of this minus sign? Cos x can be written as 1 over sec x. Then using the formula for log m over n, you will be able to write it as log 1 minus log sec x, and log 1 will be 0. So log minus log sec x you are left with, and already there is a minus sign. So it reduces to simply log sec x. So same method we are going to apply for deriving for cot x also. We will first write I as cos x over sin x. Now go for the substitution. We can put sin x is equal to t. Now if I differentiate both the sides with respect to t, then derivative of sin x is cos x, and then derivative of x is dx over dt. Derivative of t will be 1. So this gives us cos x dx is equal to dt. Now our integral is 1 over t times dt. And integral of 1 over t, just now we have seen it is log t. So it will be log t plus constant of integration. Now substitute for t. So integral of cot x can be now used as log sin x plus constant of integration. So now we know what will be the integral of tan x as well as the integral of cot x. Now in the same manner, now evaluating for integral of sec x and cosec x. We don't know which function has got derivative sec x. So we are not able to write directly the integral of sec x. So we will do some simplification here, some multiplication, division, so that we are able to use substitution and hence integrate it. So what I am going to do, multiplying and dividing sec x by sec x plus tan x. Just now one of the question we have done where we integrated this product of sec x with sec x plus tan x. It came out to be sec square x plus sec x tan x, and we were able to integrate it. So here I will, because I will be multiplying it, so we are going to divide also. Let us see, does it takes the form which can be integrated? So numerator is now sec x into sec x plus tan x, and the denominator will be sec x plus tan x dx. Now see, if I put sec x plus tan x is equal to t, and then I differentiate both the sides with respect to t, then the derivative here becomes derivative of sec x is sec x into tan x. Then derivative of x will be dx over dt, but that I will get here also. So we will take it as a common term. Derivative of tan x will be sec square x. And in both the cases, the derivative of x was dx over dt. And what about this t? Its derivative was 1. So dt we can cross multiply here. So it comes out to be same. Now look at this part. If sec x be taken common, we are left with a sum tan x plus sec x dx is equal to dt. Now compare it with your expression. You will find this is the numerator of the integral. So what is the integral now reduced to? Denominator was replaced by t, and this entire numerator is reducing to dt. So it is 1 over t dt again. See, it has taken the same form, and integral of 1 over t will be log t and then plus constant of integration. So we need to only substitute the value of t here. It will be sec x plus tan x. So the integral of sec x can be taken as log sec x plus tan x. If you wish, it can be further simplified, and the result can also be written in terms of sine and cos. But we will prefer to use the integral of sec x in this form. Now quickly solving for cosec x. Here also we will multiply and divide certain expression. You can see cosec x we can multiply with cosec x minus cot x, and because we are multiplying it with it, so we need to divide also. So multiplying and dividing by cosec x minus cot x. Now substitute the denominator t. So putting cosec x minus cot x is equal to t. Now differentiate. Derivative of cosec x will be minus cosec x cot x and then dx over dt, which I will write outside. Then minus derivative of cot x will be minus cosec square x. So this becomes plus cosec square x into dx over dt, which is equal to 1. You can see in the previous question I cross multiplied dt also, which we are going to do here as well. And what else can be done? We can take a minus sign common from here. We can take cosec x also common. So if I take minus cosec x common, from here cosec x is left from the second term, and from the first term, or let us not take minus sign common, we can rearrange the terms also. So taking cosec x common, from the next part we get cosec x, and from the first part we get minus cot x. Dx is equal to dt, cross multiplying dt. So you will find this is the numerator. Entire numerator is getting replaced by dt. And what is our integral now? It also takes the form 1 over t dt. And integral of 1 over t will be log t plus constant of integration. So simply we need to replace t by its value, and the integral of cosec x happens to be log modulus of cosec x minus cot x. But it has another popular expression which is frequently used by converting it in terms of sine and cos. Okay, you can see quickly we can write it as log. If I convert cosec into 1 over sine and cot into cos over sine, so the numerator will become 1 minus cos x and the denominator will become sin x plus constant of integration. And we can simplify both. 1 minus cos x is 2 sin square x by 2, and this is 2 sin x by 2 cos x by 2. So some common terms they get cancelled out also. This will be 2 sin square x by 2, and the denominator will be 2 sin x by 2 cos x by 2 plus constant of integration. So you can see 2 gets eliminated, sin x by 2 gets eliminated. And what are we left with? Sin x by 2 divided by cos x by 2. That will become tan x by 2. So integral of cosec x can also be written as log tan x by 2 plus constant of integration. Now with this you can see we now know integral of all the trigonometric, 6 trigonometric functions. Sine and cos we were already aware of. Only tan, cot, sec and cosec were not known. That also we have derived using the method of substitution. Now these can be used as results while in case the function comes out to be integral of one of these functions.